All right, we are a few short minutes after the top of the hour, so let's go ahead and let's do it. I am Paula Orenz. I'm a market development manager for biopharma mass spec at SCIEX. I am thrilled that you are joining us on this beautiful Wednesday. Today's agenda for Masterclass Live, one of my very favorite sessions, is about setting up and monitoring quality attributes for protein therapeutics, or a technique more commonly known as multi-attribute monitoring, or even more so MAM or MAM. Throughout the next hour, my very esteemed colleague and I will be taking you through how you can do that, MAM, to get the most out of your amino acid isomerization and localization. Before that, I want to let you know that you are free to submit questions using the chat function at the bottom of your screen throughout the entirety of the session. We'll break a few times to answer any questions that you have for us, so we want to make sure that you are leaving us at the very top of the hour with all of your unknowns identified. And if we don't get to your questions within the session, then I will happily reach out to you after the fact with an answer from one of our experts. So we'll start today's session with a brief overview of the features that we'll be utilizing. Then we'll set up the method, the actual acquisition method, and we'll close it out by processing the data with a focus on my favorite amino acid isomerization. So without further ado, I'd like to introduce you to your host today, Zhongwei Chen. Zhongwei received his PhD in analytical chemistry from the University of Wisconsin-Madison in 2018. After graduating, he joined the Research and Development Division of Regeneron Pharmaceuticals, focusing on the LC-MS-based analytical characterization of biotherapeutics. He joined SCIEX, thankfully, earlier last year as Senior Application Scientist to support the biopharma market. In this role, Zhongwei is responsible for preparing and delivering customer demonstrations, as well as developing applications that show SCIEX LC-MS product features in biopharma workflows, including peptide quantification, intact mass analysis of MABs, HCP analysis, and peptide mapping. And today we are going to see his MAM skills in action. Zhongwei, thank you for sharing your expertise with us today.
Thanks, Paula, for the introduction. Hi, everyone. So welcome to the SCIEX demo lab in Redwood Shore in California. So sitting right beside me is a SCIEX latest high-resolution mass spectrometer 7600. So in this session here, I'm going to talk about how introduce you to the 7600 technology, especially the EAD, and also the software we are going to use to process the data. So I have prepared some slides first to have a brief introduction. So let me move to my PC. So before we jump into the actual data, so data acquisition, so I like to give you some information on the 7600 system, on the technology we are using today, and also the tools we're going to use it. So here I have a MAM EAD peptide mapping workflow. It's a very typical peptide mapping workflow, starting from a sample preparation, where we will use the enzymes such as trypsin to digest the proteins or antibodies to get the peptides. And then we will inject the peptides into the LC-MS. Here you can either use the CID or EAD. So in the workflow we are going to talk about today, we are using the EAD, which can provide more quality attributes such as the isomers to you. And so the first step will be the data processing using the, here we are using the SCIEX Biological Explorer for the database search to get the IDs. And also the, it can also give you the relative quantitation of what's the level of the PTM. So let's first talk about the EAD part. The EAD, it's electron-activated dissociation. In short, the mechanism is that the free electrons will be captured by ions and to form a intermediate radical state, and then the fragments will be induced. The fragments, the CZ fragments will be the major fragments, but also there will be some minor BY and AX ions. And so the electrons generated here, we have a two-level energy. So on the right side, we have the energy that can range from 0 to 25, which gives us the capability to cover different fragmentation regime, including the ECD, which is the KE equals 0, and hot ACD and EIEIO. So different fragmentation regime can help us to better analyze different molecules, such as including the multi-charged peptides and proteins, and also the glycopeptide, disulfide bound peptide, and the singly charged molecules. And here, this slide, I want to show you how it's looking inside the 7600. Here is the diagram inside. On the left side, it's the ion source. Passing from the ion source, we have the Q0 and Q1 and Q2 and zero trap, and all the way to the top detector. So the EAD cell is located right between the Q1 and Q2. Here in this figure showing here, the precursor ion is traveling in a horizontal way from Q1 to Q2. For the electrons, it's traveling through the vertical way. So the electrons will meet with the precursor ion just in the EAD cell to induce the EAD fragmentation. And then the fragments will be transferred to Q2 and zero trap and to top detector. On the left top corner, we have the live picture of the EAD cell. And so right after EAD cell, we have the traditional CID cell, which is the Q2 here. And so the speed of fragmentation of EAD is quite fast, benefiting from the electron capture reaction time, which is typically in the range of 10 to 30 milliseconds, and which makes it compatible with the DDA on LC time scale up to 20 Hertz. And also the EAD technology we have here, it's reagent free. It's unlike ETD, which requires the reagents, which requires quite some maintenance. But here we are solely reliant on the electrons. And also the EAD, it's reproducible at a quantitative level, and it is optimized to limit secondary fragmentation, and there's no need for further activation of charge-reduced species by CID. The data processing software we are going to use today, it's the Biologics Explorer software 2.0. This software, it's used for therapeutic protein and antibody calculation. There are many two workflows provided by the software. The first one is the intent and subunit analysis. By using this software, we can get the accurate molecular weight of either the mass at the intent level or the subunit after reduction, or after using some enzymes to break the antibody or proteins into smaller pieces. The second major workflow is the peptide mapping. The software can help you to identify all the peptide and as well as the PTMs, which is at low abundance. So one highlight of the software is that it can not only process the CID data, and also it process the EAD data. And besides that, it can also process the PTM analysis, such as the disulfide bonds, the N-glycosylation and O-glycosylation. So in this software, we have embedded N-glycan and O-glycan library, which you can use for the database search. And also, this software provides a comparative studies, such as you have different stress, like pH stress or heat stress, or even from different benches, you can do side-by-side comparative studies. And the other software we'll be using is the SCIEX software. So today, we will be coupling SCIEX with the Biologics Explorer for the relative quantitation of the quantity attributes picked up by the EAD. And so the Biologics Explorer software 2.0, it supported the high resolution mass spectrometer. In SCIEX, we have a different generation of the high mass accuracy or high resolution top mass spectrometer, starting from 6600 and to the X500B, and to our latest 0-TOF 7600. So the EAD technology is only available on the 0-TOF 7600, which we'll be focusing today. So the software also supported different the file formats for wave 1 and wave 2. Because for the previous generation of the software and instruments, they are producing the wave 1 file. So the latest is providing the wave 2. So the software providing both access to the 2 files for the data processing. And so as I mentioned, so this supported both CID and EAD. Okay, so this is the introduction part. So I will hand the time to Paula for our first QA.
All right, Jungwei, I've got a couple of questions for you, and I'll take this opportunity to remind everybody, please feel free to send us any questions that you have. We will have 2 more breaks, I think, for questions before we close out for the day. So plenty of opportunities to get your questions answered. So to start, Jungwei, can you use EAD with MS1 only?
Yep. Yes, the short answer is yes. Because EAD it's a fragmentation technique. So you can when you are setting the MS methods, so you can actually turn off the you can just acquire the MS1 data and so then that's basically it's a MS1 data. But if you turn on the EAD, adding the kinetic energy to induce the time for the fragmentation, then it can provide you the EAD fragments.
Okay, awesome. So next question, where do the electrons come from in EAD, and do they need to be calibrated?
Yeah, that's a great question. So actually, we have two filament lines there to generate the electrons. So there is in the tuning page of the SCIEX software, later I will talk about there is a tuning procedure for the calibration. So once there is, if it's has been running for some time, if we found the kinetic energy is not sufficient to generate a good fragments, then you can go to the tuning page and to do the calibration. And so we have a backup electron generator there. So if after like a year or 2, if somehow the first generator failed, you can always use the backup generator for the EAD experiment.
Awesome. Backup is never want to use it, but you have always got to rely on it at some point. Okay, maybe last question for now. Is the EAD energy something that has to be optimized regularly?
For the EAD, yeah, actually that's also a very good question. So there are different applications. So if we are talking about the peptides, actually we have one tech loads that compare the different K energy from the lower end, like 0 to 1, to the middle end, 7 to 8, all the way to more than 15. So we found out 7 works best for the regular peptides with different charge states, and for the glycopeptide, and so it's and also for the isomer, which we'll be going to talk about today. And so it is only for some like rare cases, such as for the singly charged peptide, like the sulfated peptide, then you will increase it to a higher energy end, like more than 15. But for the rest of the peptide, only 7 works best.
Perfect. And that goes for therapeutic and digested peptides.
Yep.
Okay. All right. So I said that would be the last question, but I'm going to hit you with one more, Zhangwei, because we've still got a minute or 2 in this session. So is the energy of electrons the only parameter for EAD fragmentation?
Actually, yeah, that's what we will be talking about in my next part. So there will be a few parameters we'll be talking about, including the kinetic energy and also beam current and reaction time. So I will save that part for the second. I will show you in the SCIEX software. That will be that will be more clear. Yep.
So Zhongwei, shall we use that as our transition into the next section?
Yep, that would be great. Okay,
Okay.
so let me share my screen here. Here we go. We have a SCIEX software here. So since we are talking about the EAD parameter, so let's just jump to the MS methods and then go back starting from there. So here we can see we have the EAD fermentation mode. We choose the EAD here, and so there are many parameters here, but for most of them, they are shared with the CID, such as the start mass, the mass range, accumulation time, the decarbonization potential, or condition energy. So the parameters that are unique to the EAD is the electron kinetic energy we are talking about here. So here I'm saving here for the MAM experiment. And for the second parameter that is very important, sorry, that's me. It's electron beam current. So you need it ranges from 0 all the way to the 9,000. The optimized value we get for the peptides it's around like 5,500. But this parameter it's less compared to the KE. It doesn't make that significant changes in terms of the fragmentation. The KE will be the most important, but the electron beam current can affect the intensity of the fragments we generated. And so another parameter we have is here. Sorry, I have we show down some parameter here. Another parameter we have is reaction time. Typically, it's in the range of 10 to 30 milliseconds. If you have some molecule that is very difficult to fragment, and the fragmentation efficiency is low, then you can try to increase the reaction time to 20 or to 30. And so these three parameters are the most important EAD parameters here. So let's go back to the to the main page of the SCIEX software. So to give you an overview, we have three parts in the SCIEX software: the data acquisition part, the data processing part, and the management. So in the acquisition part, you can set the LC methods, MS methods, and doing the MS tuning. This is where we will, if there is a need to calibrate the electron generator, we will calibrate it here. And also there is a mass calibration, it will be also here. And then we can submit the bench in the bench module here. And in the data processing, we have the Explorer to look at the raw data, and analytics to do the quantification, which we will be using later for the quantification of the quality attributes. And for the third part here is the management. We can manage the LC, the mass spec, and also there's the event log that records everything that happens on the instrument. So which is very useful for the troubleshooting. And so let's go into the LCM method to set up the LCM method first. So here we have the pump. We will set the flow rate, the initial gradient here, and the most important one is the gradient. So this is the gradient I set for the MAM experiment. Basically, it's an increasing of organic solvent B from 25% to 40%. And the first few minutes, it's just getting rid of the salts, detergents, and it is going to the waste. Then we will set up the rinse settings, the purge settings. And after that, we will set the auto sampler. Here I'm setting 5 degrees. And then for the column oven, we have I'm setting 40 degrees here. So I'm using a CSH setting column, which is 15 centimeter long for this experiment. And for the valve mode, it's when it's in position A, it is going to the waste. So here I'm setting the first 5 minutes go into the waste. starting from the 5 minutes, it's going to the mass spectrometer. So at 65 minutes, it will go to the waste again. Basically, it means our signal of the peptide will be in the range of 5 to 65 minutes. So that is the LCM method. Then this goes to the MS method. The MS method here, there are different already embedded workflow for different molecule. You can choose small molecule peptides, intact protein, or glypeptides. So here, what I'm choosing is the peptide, and there is a method duration for the acquisition time, and the source and gas parameter, which because here we are using 0.25 mils per minute. This parameter are good because the source parameter are majorly depend on what's the flow rate you are using, and the temperature here I'm using a 450 degree. Then the experiment here we are using the IDA experiment. IDA is just another name for DDA. It's data dependent. And we choose the polarity and the spray voltage, and also the mass range, and also declaration potential and condition energy. So the condition energy at MS1 level, it is used only for the transmission of the molecule. It's not for the fermentation. And so the DP spread and C spread here, it's more like a stepped energy. For example, if you are set DP spread 10 here, then the declaration potential will ramping from 75 to 80 to 85. And the accumulation time, we are setting the 0.1 seconds. This is determined by what's peak width you have. Changing this parameter will finally affect what's the cycle time you get, and finally it will affect how many data points can you get across a peak. And here for the sorry. So for the peptide, for the time beans to some, typically it's we will set from 8 to 10. And for the channel, it's this channel here. It's a top detector. We have 4 channels. It's these 4 channels will take turns to receive the ions to make the best use of the cycle time. And ideal criteria, you can also choose the molecule you are analyzing. Here we are using the peptide. And here for the maximum count ion, it's we are set 10, which means the in each peak here, the top 10 most abundant ions will pick out for the fermentation. And intensity threshold, I'm setting 125 here. So anything between 125 will be ignored. It's mainly used to get rid of the noise. And here we have the dynamic background subtraction to minimize the noise effects, and also exclude the former candidate ion to make sure we pick up the low abundant ions. And then we have the charge states. The peptides mostly they are in the range of 2 to 10. And isotope to select here, you have choice to set monoisotopic or the most abundant intense. I'm choosing the most intense one. And then it goes to the top MS2 parameter. As I just introduced a moment ago, the most of the parameters are similar to the CID, like the mass range, the declaration potential. It's just the electron kinetic energy here, and the electron beam current, and the reaction time that will be different. So this parameter set here, it's good for the peptide mapping experiment. Unless you have some specific cases, such as the synchrony charged sulfated peptide, you may need to increase this K energy to like 15 or higher to generate good fragments. But for the electron beam current, the reaction time, I found it's good. And for some of the like harder molecule that is difficult to fragment, you may trying to increase its value to find out the best parameter there. But once again, for most of the cases, this parameter works fine. Actually, we have a tech loads that compare the different parameters for different molecules. Okay, so I will stop here and pass the time to Paula for next QA.
Okay, Zhangwei, I've got a couple of questions for you. I think some of which you already answered just through your explanation, but if you don't mind, I'm gonna go through and ask them of you anyway. So you said that 7 EV is good for peptides, and you even just said that you might have to increase it to about 15 for cyclic peptides, but is 7 EV still suitable for singly charged peptides?
For singly charged peptide, nope, we have to increase it to a higher energy, like 10, at least more than 10, like 15 or even 20.
Okay. All right. Do I have to separate different IDA runs for optimization of KE, or is there a more convenient way to optimize the EAD parameters for the molecule?
Yep, that's a very good question. Actually, so to find the best parameter, actually you can use another acquisition mode. We call it MRMHR. In the MRHR mode, so you can in a single run you can set multiple parameter. So in one run, actually in one run, I said before, I said like 16 parameter for that single molecule. And so different, you can try different KE, you can try different reaction time, and you can try different beam current. And so every parameter is in that run, then you can just optimize it just by that single run.
Okay. Next question. Can you elaborate on the effect of EADRF?
EADRF, yeah, for that value, it generally will affect the transmission efficiency in the low molecular weight ions. And so 100 is a value that we found that works best in terms of transmission of the low molecular weight ions. Generally, so for our application for the peptides of the proteins that I have run, or even for lipids and oligonucleotides, it's the value we use. So I didn't choose. Actually, I didn't change it for the application I have been using.
So for this application, you didn't adjust it?
No, I didn't.
Okay. All right. Let's do another question here. Can you ramp the EAD energy?
For the EAD energy, yeah, the way you ramp it is to like set it in different like in MRMHR, like comparing different energy to generate different the fragments. But you cannot just like use like a stepped energy like the DP and get it in one spectral. We have to set it in a separate acquisition channel.
Yep. So basically almost like different injections, different methods each time to ramp it. All right. Do you need both KE, so the kinetic energy of EAD, and collision energy?
Collision energy. So because in the MS1, there are two collision energies. It's at MS1 level and MS2. At MS1 level, the collision energy we set at 10. It's basically for the transmission of the ions. So at MS2 level, when we are doing the EAD, in the collision cell energy is also kept at 10. It's only solely used for the transmission. It's unlike in CID. In CID at MS1 we also set 10, but at MS2 we are setting like 20, 25, or 30 or something to fragment the ion. So to summarize, in EAD the collision energy either in MS1 or in the Q1 or in the Q2, it is solely for the transmission of the ions.
Okay. All right. I've got a couple of other questions to ask, but I think at this point we can hold them and move on to the bread and butter of what we're here for today, and that is data processing.
Okay, great.
I guess that would be meat and potatoes is like the actual bulk of the meal, not bread and butter.
Yeah.
Sorry.
Then let's jump to it. So let me share my screen here again. So the third part here will be the data processing. So before I show you using the software for the data processing, I want to show you how the raw data looking like. So basically we have the blue color is the MS1. You can tell from the title here, the EAD MS1, and the red trace is the EAD MS, the EAD MS2. So it has different channels here. If we go to the TIC, actually we have channel 1, MS1 from 200 to 2000, MS2 from 100 to 3000. The reason we have a 10 like MS2 channels here is because we are set top 10 method for the DDA. And then let's move on to using the software, the BE software for the data processing. So here, just an overview, high-level overview of the BE software here. We have three major sections. This section, it's a file menu. You can either save the workflow you used or export the results, or doing like set some preference of the software. And in this tools menu here, we have some small tools such as mass calculator, library browser, where you can browse the N-glycan or O-glycan library, and instrument editor, where you can edit the fragmentation you are using, and the modification editor, where you can specify, you can find the embedded PTMs, and also you can add your own customized PTM, such as you have a labeling reagent, customized tag, etc. And for the enzyme editor, there is also already embedded enzymes such as trypsin, asparagine, glucine, etc. And also you can just add an enzyme. And for the package manager, it's basically manage all the workflows. If there are new workflows that coming out, you can go to the package manager to download the workflow. And in this section here, it is where we will work most to set up the parameters for the workflow. So from this folder, templates, the templates folder contains all the workflows we have. So we have two major workflows. One is the intact workflow, one is the peptide mapping workflow. And so this time, because we are using the we are doing the MAM EAD, so we are using the peptide map simple workflow. If you have both N-glycosylation and O-glycosylation, you may want to use the peptide map extended workflow, or the disulfide or scrambling peptide analysis. The peptide the extended workflow basically has two searching nodes. You can search like one load for N-glycan, the other load for O-glycan, and etc. And so let's take a look at the workflow, the peptide map simple workflow we are going to use. If you double click, this workflow will just come out like this. And so in the first impression, so this is more looking like a waterfall. So we call it a waterfall workflow because it's, you start loading the data in at the top, and your results will come at the bottom. And also for every step, it's totally transparent to you. You can actually run each step separately. So in that way, you know what happened to your data after each step. On the left side, it's an explanation of what each loads do. For example, for the first two loads, it's basically loading data and select the useful retention time range. And for the third and fourth one, it's analyze and annotate features. And so let's try to load the data. If you double click, then you can select the data here and load your data and click OK. So after loading your data, we can click, if you click this one, it will only run the first load. But we also have a starting button, which is here. if you click this button here, it will start every load. So like in terms of the method, in terms of setting up the first run of my data, I always like use the separate one to make sure I got the right parameter for each step. So if you see a green check here, which means the step is done, and then you can double click. Then it will bring you iron map that shows you what does this step do. Basically, this step is just loading the data. But for the second load here, rotation time range. So here I will be setting 5 to 65 minutes to save some computation time, and then click. Now you can click open. Now you can see we are for rotation time. We are just cutting the range that has the peptide signal from 5 to 65. And so for the next load here, data preparation. So data preparation basically does the noise removal, peaks and clusters and groups, and it also process the MS2 information. So there are many nodes here, so it may like look like intimidating, but actually the default settings works pretty well, and we don't unless you have like some very special cases. For example, you get a very high noise, you may want to click open to set the noise threshold, but otherwise this parameter just works fine. I usually will start the default parameter and see how it looks, and then go back to it to change the parameter if there is a need. So and the next step, the peptide mapping, we double click, then it brings us to the temp here. This temp here is it's a major parameter we'll be setting. We will set the mass tolerance for at MS1, and at MS2 we will choose the EAD, because here because EAD can differentiate the amino acid isomers. I'm setting the EAD isomer fragmentation here, and here we will set the mass tolerance at MS2 level, and also a score cutoff for your peptides. And then there is a sequence information we will set. You can either use text or use a FASTA file or use some other method. The most common used one will be the first two. So I'm setting like heavy chain and light chain for the list map, and this one. And here you can set up the enzyme you want to use. So we are using the trypsin here, and then the maximum mixture cleavage and the minimum peptide length. And also for the modification, we have the fixed modification, where you can select, you can do like a quick search, and also you can like make it your favorite one, and then next time it will just appear at the top. And for the variable modification, these are the modification, common variable modification we set, but also you can add some other modification here. We have tons of embedded modification. And so the B software is also capable for sequence variants, which is another workflow we don't have time to cover today. And so for the glycosylation, you can either choose no glycosylation if it's treated by PNGCF, or choose the glycosylated one. And for if you choose glycosylated, there are different glycan database. You can choose the GlycomDB, the small true cell database, the larger database, or O-glycan database. And then after choosing that, you will allow sites only unlinked or only O-linked or both. And if it's for unlinked, there is the consensus sequence motif, which is the NXTLS. And also you can even set the glycan modification, because some glycans they can carry methylation or acetylation and etc. It's so the BE has this flexibility. And the next term is disulfide bond. If you are doing non-reduced pair mapping, you will set you will define the disulfide bond here, but for the MAM workflow we are talking about today, it's the sample is already reduced, which means for disulfide bond, we just simply choose long. Then after setting it, we can click OK. Oh, and also, by the way, another note here, if you want to find the definition of each parameter here, actually you can click the show help. It will bring you to an online menu, and basically it tells you what does it mean, like the MS tolerance, like the ignore annotated features. What does each parameter mean? So this is actually very helpful when you set all these parameters. So let's go back to be here. And so once you are set, you click OK. And the next time will be review results. Review results, it's we will just put the sequence again and click OK. So after that, you can either start the data processing one by one, or start the whole process all together. Actually, for the results export, you can export to SCIEX for the relative quantitation, or we can save it as snapshots for later on review the data purpose. So then let's take a look. In the interest of time, I won't run it because it takes some time. I have run it before. It takes around like 7 or 8 minutes, depending on how fast is your computer. And so I have results already ran here. So we can go to the review results. We just double click. Then here comes the results. So the reason why you see a single peptide here is just because I rejected. I'm choosing one peptide as an example to show you. But here, just let me quickly close the review and let me quickly run another run to get all the peptides here. Okay, here we go. This is all the peptides and its PTM identified. So there is actually a lot of information here. But let's break down it one by one. On the left upper side, we have the all the identified peptides. It basically shows you the overall sequence coverage. And if you click on the identified peptide, because there can be some miscleavages. If you click on it, then the annotated peptide spectrum will be showing on the right. And at the bottom here, it is showing the different charges. For example, for this peptide identified, the charge 4, charge 5, charge 6 are confidently identified. And because for each peptide, there can be some variants. For example, for the peptide without PTM, for the peptide with PTM, for example, here we have a methionine oxidation here. So all the different peptide form will be showing in this peptide map table here. And so that is for the peptide mapping table. And for this table here, it's the for this table, it's contains all the information such as the peptide sequence, the modification, what's the intensity, etc. So this for this time, I want to show you use one peptide as an example. With this peptide that has the D and I30 isomer, because one of the unique advantage of EAD is it can pick up these quality attributes that cannot be picked up by the traditional CID. So here I'm using this peptide to as an example. So this peptide here, we have one D amino acid here and one N here. So there are two types of isomerization. This D can be changed into I30. So actually we have isomer detected here. So if I choose this two, this smaller peak is the I30, and this peak is the D, which is the most abundant native peptide. How can we tell this peak is I30? Actually, we can zoom in the region this we have the diagnostic sign for the ICD, which is minus 57. So that's why we can tell. But for the other peptide, for the native peptide, we don't have minus 57. And that is the first isomerization. The second isomerization is for this peptide, there is a asparagine. It can go through deamidation and to generate D or ICD. So here, actually, we observed three peaks in the it's these 3 peaks here. So after identification, we found out the first peak and the third peak is the ICD, because the first peak it generates the diagnostic eye of also minus 57, and at the third peak also we have the minus 57. The reason we have 2 peaks here is that one is in L form, one is in D form. So the other one, this peak here, we don't have minus 57 loss, so we tell us it's just the D. So these are the 5 like isomerization forms we observed for the peptides. And so how can we quantify it? Then we will export it into SCIEX for the accurate quantitation, because SCIEX allows you more flexible integration. So what I will do is to turn on the review mode and just check these 5 peptides and then reject all other peptides and then save and reload. So now it will process again, and if when we open it, there is only 1 peptide that will be kept. This is just as an example. So in the real practice, you can like double check to make sure you get all the peptides you want, and then save it. So this is so I'm using this single peptide just to demonstrate. So after that, we will export to SCIEX. So we hit export, and after export, it will the export file will be like this. It's a text file, so I'm copying it to the Excel. So for the export information we can get, it's the group name, it's basically the peptide sequence and the different peptide, the PTMs, the isomerations, and what is the accurate mass for that specific peptide PTM, and also what's the retention time. With this information, then we can go to SCIEX into the analytics module, and to set up the quantitation method. This is the results I get, but let me show you the method I'm using. So this is the method. First, we will choose the sample and then the components. So all this information I just copied from the BE software we get a moment ago. So here we will have different isomerization form and the accurate mass and also the rotation time. And so the next time is the integration. So for the integration, we can double check if the integration looks good here. You can change the parameter on the left side. And so we are not using library search for the MAM workflow. And for the calculated columns, here I'm setting what's the area for each isomerized peptide and what's their percentage. And then here are the results we got. So for this MAM experiment, we are doing a heat stress sample for the NIST MAM. So we have a control sample in triplicates, and heat stress for 1 day, heat stress for 2 days, and 7 days, and 10 days. Using this way, we are expecting the deamidation will increase. And so on the left side, let's this all components. For each component, we have different charge states. So let me click the L, ICD. In this way, we can, on the left side, on the right side, we have the percentage. So For example, for the percentage of L form of ISRD, we can from here we can tell, because we when we have longer heat stress, the percentage is increasing. How about the isolation of D? Isolation of D is also increasing from 0.01 all the way to 1%. And at the bottom here, we have the XIC here. And so you can always adjust the integration parameter if you don't, or if you feel it's not good. And so to summarize the results using a slides here, the EAD is definitely able to picking up these quality attributes that cannot be picked up by CID, because EAD enables the differentiation of ISRD and D. And so here we have 5 picks for these 5 different forms for this peptide: the isomerization of D, the native peptide, the air form of ISRD, the D after deamidation, and D ISRD. And on the right side is the glycosylation. And so after 10 days of heat stress, we can see our last trend, because the heat just promote the deamidation. And so we are able to quantify. If we solely running a CID, you can only see just one curve of the deamidation. But using the EAD, we can tell how the ISRD or D isomerization changes. Okay.
Also, Zhangwei, I'll throw this back to you. Can I customize a specific modification in Biologics Explorer?
Yep. So I have briefly touched it in my previous introduction. So in the tools menu, there is a modification tab. You can either put a chemical formula there to or put the math there to customize the tag. So after you put in there, when you set up the possible modification in your peptide mapping search, you can choose it. So yeah, it's quite straightforward. You just need to remember it's actually in the left corner. It's in that area to yeah.
Okay. All right. Next question: is there any way to make the figure look more clear in terms of the annotations on the peaks?
Yes. Actually, in the BE software, in the mass spectral annotation window there, actually one of the trick I found is that you can make the window floating. In that way, you can adjusting the window size, and when you adjusting the window size, the fonts and the overall spectral size will change, and then you can find an optimal size that is best suited for your presentation, and then you will make it look very nicely. Actually, to prepare my past ASM poster, I used it that way, and so it works very well for me.
Excellent. Okay, it is clearly time for us to let everybody get back to their afternoons. I want to thank you all so much for joining us this afternoon or this morning, depending on where you are. Sorry about Pip in the background. And hey, we are hosting a couple of other master classes in the next couple of weeks. And very shortly, we will be announcing the next rollout of master classes that you can look forward to. We're going to switch it up from protein therapeutics to mRNA-based therapeutics. So I hope you will be able to join us in the next couple of weeks. And maybe we'll see you at some of the trade shows that are coming up shortly. So thank you again for your time today, Zhangwei. Thank you very much for your expertise and for taking us through the workflow. It was really wonderful.
Thanks, Paula. Thanks, everyone. Have a good day.
Thank you. Yep,
Bye.
you too.